Hello everyone, welcome back. Today I will going to the for the last part of the colloidal dispersions according to the Bpharm syllabus of PCI. Okay. In previously we have already completed different properties of the colloidal dispersion types and all those things. Okay, according to the syllabus. So today is the last part of the colloidal dispersion, and today I will start with the effect of electrolyte. Means you can just a little bit understand by this kind of heading only. The effect of electrolyte means if we add some electrolyte, if the concentration of the electrolyte is increased, so then what will be happen? If the concentration is increase, then what will be happen? And if the concentration is decrease, then what will be happen? How it can be affect the stability and all those things. That is the basic principle, and that is the basic discussion in this effect of electrolytes. So you can see that effect of electrolytes actually divided into three part mainly. Like first of all, the one theory you can see the DLView theory, and what is DLView theory all about I will discuss. And after that, that is the Hofmeister or Lyotropic series, and the last one is the Schoolje-Hardy rule, or you can call it like a Hardy-Schoolje rule also. So okay. So first of all, the first one is the DLView theory. So DLView, the word actually comes from the scientist who have described this kind of theory, like Darjaguin, Landau, Varroy, and Overbeek. They have proposed this theory. So according to this theory, I will just going with the line by line. So according to this theory, the distance between two dispersed particle mainly influence the particle-particle interaction. Obviously, if we consider that one part dispersed phase have positive charge and another dispersed have the negative charge, obviously there should be some attraction force will be acting. And if you consider the negative, like negative charge is present in dispersed phase, and another dispersed phase negative charge is present, obviously their repulsion will be predominant. So that's why this line actually stated like that. And after that, using this theory, one can approximately determine the amount of electrolyte required to precipitate or stabilize a colloid. So we can also just get little bit idea that what is the approximate electrolyte we have to add, so that the colloidal particle, the dispersed phase, they can precipitate, okay, or stabilize. If they are precipitate, obviously it is unstable condition. If there is no precipitation occurs, all this dispersed phase in a proper disperse mode, then it will be a stabilized formation. So how much electrolytes actually needed for the stabilization, for the precipitation, all those things can be get little bit idea from this kind of DLView theory. And after that, in the colloidal dispersion due to the Brownian movement, I have already discussed in the kinetic properties of the colloidal that due to the Brownian movement, what happened? The dispersed phase, they actually move randomly, or they can just collide with the container wall of the container and with each other, so that they will not settle down under the influence of gravity. So stability can be maintained. So that is the very basic principle of Brownian movement, and there should be some particular size range is mentioned, that above this kind of size range, the particle will show the Brownian movement. So here it is said that in colloidal dispersion due to the Brownian movement, frequent collision between particle occurs. So that is also an idea we can get from this kind of DLView theory also. There are two types of interaction occurs, that is repulsion and attraction. I have already mentioned, if the charges are opposite, there should be some attraction. If the same charge is present, the repulsion actually predominant. So this is the basic things. And after that, in the next slide, it is written that the low electrolyte concentration. So that is the main important point, that what is the effect of electrolyte. I have already detailed in the first slide that if we add the electrolyte, means there is the concentration of electrolyte is increased. So what will be the case? And if the electrolyte have a little bit lower concentration, what will be the case? So you can see here that DLV theory proposed that stated that in low electrolyte concentration, repulsive forces predominant. Particle experience repulsive force upon approach, so they will be dispersed. Try to understand, if there is a repulsive force is present, like the dispersed phase have same charge, like negative negative, there should be some repulsive force will be acting, and that cases they will not agglomerated or aggregated, and they will not settle down. They will properly disperse. They will properly disperse in the dispersion medium, and that is the cases of any kind of proper stable colloidal dispersion system. So here actually this is only just mentioned that if there is a repulsive force is present in the low electrolyte concentration, their dispersed, the dispersed phase will be predominant, or we can say the dispersed phase over this kind of settle down or precipitation. Okay, and when the repulsion is more than the particle rebound after collision and remain individually dispersed. So that is the concept, that if there is a repulsion is present, so they will be obviously individually dispersed. There is no attraction force will be acting. And in the high concentration of the electrolytes, the case is actually opposite. Electrical double layer diminished. We have also already discussed about the electrical double layer concept. So if the electrical double layer diminished, if the double layer actually get lost, so as a result the van der Waals forces will be acting, yeah, and if the van der Waals forces is acting between any kind of dispersed phase, so there is attraction force will be predominant, and due to the attraction forces you can just easily understand, due to the attraction they will agglomerate or they will aggregate, and due to the aggregation coagulation obviously happen, and after that it leads to the precipitation also. Okay, so that is the case. And if precipitation is happened, so this leads to the unstabilization of the colloidal dispersion medium. Okay, when attraction is more than the particle adhere after collision and aggregate. When attraction is more, so then particle will adhere with each other. They will aggregate to each other, and they will settle down, okay, after the collision. And the last line that is important from DLView theory, that we need repulsion more than attraction to get stable. When I have discussed in the earlier session also, that I have already told there also that in colloidal dispersion repulsion should be predominant than the attraction, between the dispersed phase particle. So you can easily understand, then the charge, obviously dispersed phase particle have the charge in their interface. The interface theory also we have studied. So if they have the similar charge or the like charge, so there should be some repulsion force will be acting, and that cases they will form a stable colloidal dispersions. So this is all about the DLView theory. Okay, so next one is the Hardy-Schulze rule, or you can call it a Schulze-Hardy rule. So what actually is stated? The rule states that the amount of electrolyte required for the coagulation, coagulation means also is a kind of aggregation, agglomeration. Okay, so this is the kind of same process, like you have heard about the blood coagulation. So this is little bit different concept. Still you can call it like a agglomeration or aggregate, this kind of thing, that the amount of electrolyte required for the coagulation of a definite amount of colloidal solution is dependent on the valency of the coagulating ion. Okay, so if the valency is more, so you can see here, if the valency is more, the greater the precipitating power. That is the important line from the Hardy-Schulze rule, that if the valency of the ion is more, the greater the precipitating power. Valency of the ion means the electrolyte that will going to be added, like in maybe aluminium, magnesium, sodium, this kind of thing. Okay, like if you follow the example, you can clearly understand that Al3 plus is more effective than Mg2 plus or Na plus. Like you can just written like that way, that Al3 means the valency is 3, then Mg2 plus, okay, Mg2 plus, and last the ion electrolyte will be sodium plus. Okay, that is the precipitating power. So if you add the aluminium, so the precipitating power will be more compared to the magnesium if you add the magnesium, and if you add the magnesium, the precipitating power will be more compared to the sodium, because the valency for Na plus is 1. Okay, like that way. So this is that is the point. And after that is stating that hydrophobic colloids need very small amount of electrolyte for coagulation, but hydrophobic means the compound or the colloids which we hate or have a fear towards the water, so they will actually need very small amount to coagulation. But if I consider the hydrophilic colloids, they need a larger amount of electrolytes. Why? Because the hydration layer, as it is hydrophilic means water loving, So as it is water loving, so there should be some hydration layer is present. So to get rid of, to get over this kind of hydration layer, okay, so the surrounding the dispersed particle, so the electrolytes should be, concentration will be more compared to the hydrophobic layers. If I try to coagulate this particular dispersed phase, okay, so that is the all about the hard disk culture. It completely depends upon the valency of the ion, that how the valency, in a particular colloidal dispersion medium, if you add the Ag3 back, okay, aluminium, then it will be precipitated more compared to the, if you add magnesium, and if you add magnesium, it will be precipitated more compared to the sodium. So according to the valency, the precipitating power can be vary. The more the precipitating, more the valency of the ion, the electrolyte, the greater will be the precipitating power. This is all about the Hardy-Cool's rule. Okay. So after that, the next one is the Hofmeister or the Lyotropic series. So this is all about kind of same, that lyophilic and association colloid. Lyophilic means who have the affinity towards the solvent. Don't mix up or don't just get confused the lyophilic with the lipophilic. Lyophilic means the solvent loving colloidal dispersion, and association colloids means like a surfactant or surface active agent. So they are thermodynamically stable. Because they are, why they are thermodynamically stable? Because all those entropy, enthalpy, they will be actually in a proper way, because the proper affinity towards the solvent system and the proper solution is actually prepared, we can prepare. So that's why this is actually thermodynamically stable, and they can exist in the true solution form also. So they do not coagulate on addition moderate amounts of electrolyte. Means if you add little bit amount or moderate amount of electrolytes, the lyophilic or association colloid, they will not coagulate. However, if you add sufficient amount of electrolyte, then only they can coagulate, and the term is actually known by the salting out. Okay, so for this kind of lyophilic and association colloids, so you have to added more amount of electrolytes so that they can coagulate. Actually the terminology known as the salting out. The coagulating power is lyophilic colloids may be given, actually they have given by the Hofmeister and Lyotropic series. Now how the series actually varying, that you can see here, that the power of the different types of electrolyte decreasing order. You can see the citrate, okay, after the tartarate, after sulfate, acetate, chloride, nitrate, bromide, iodide. So this is the decreasing order of, okay, decreasing order of precipitating power. So obviously you can see here that how this kind of this is little bit concept with the this kind of valency also. So this is the series of Lyotropic series. Now the precipitating power is due to the ability of dislodge solvent sheath from the colloidal particles. So the precipitating power, this is actually depends upon the ability, so then they can dislodge the solvent sheath from the colloidal particles. So this is all about the Hofmeister Lyotropic series, you can understand. Okay. So it was all about the effect of electrolytes, and now the last topics from according to the syllabus, that is the interaction of colloids. So in the syllabus actually sensitization, Quas, those are there, but you have to understand the protection, mutual precipitation, all those things. Okay, so I will just go one by one. So this is the interaction of colloids. If the colloidal particles, one is hydrophobic, one is hydrophilic, this kind of thing, if they have to interact with each other, what can be happen, or how we can be stable one colloidal dispersion, how can we unstable one colloidal dispersion? Obviously our desire or main goal is to stabilize one colloidal dispersion. So I will just discuss you all those things. Okay, so first one is the mutual precipitation. So you can just see here in the slide that when two oppositely charged hydrophobic colloids are mixed, mean one have positive, you can see here one have positive, one have negative, then what it will be hydrophobic, means the water heating, then the precipitation takes place. How? The charges necessarily for stability get neutralized, okay, and with each other, and the attractive force will be more. Means try to understand, when there is a different kinds of property, different charges present. So I have already discussed, if the charge is like negative or positive, then there should be a repulsion force and it will be dispersed properly, no settle down or no precipitation will be happen, means this is the stable formation. But if there is a unlike charge like positive negative, obviously there is a the attraction force will be dominant. So due to that, the charges that is necessary for the stability, that will get neutralized and the precipitation will be takes place. Okay, so means like colloidal dispersion will be like that, they will just mixed up and the precipitation will be happen. Precipitation will be happen. Okay, so that is the mutual precipitation, and mutual precipitation, obviously this is not a stable condition. Try to understand, mutual precipitation, this is not a stable condition. Okay, mutual means if there is some common things is happen, if you add different charge, but they will togetherly precipitate. Try to understand what is the common between them, that they will togetherly precipitate. So that's why the terminology is like that, the mutual precipitation. And if there is any kind of precipitation is happened in the dispersed phase, so obviously the stability will be get hampered. Okay, that is the concept. So after that, the Quas-Svate formation. Quas-Svate means, if I tell in a very easy language, Quas-Svate means there is a two different layer will be present. Immiscible layer will be present. Okay, immiscible layer will be present. Means one layer having the different types of property colloids, and one layer will be having the different types of colloids. So there is a immiscibility will be actually happened, or the immiscibility will be can be observed. So just try to focus on these things, that when oppositely charged hydrophilic colloids are mixed, a colloid rich layer separates, which is called as colloid Quas-Svate. Means if we add some charges, opposite charges in a hydrophilic, then colloidal rich layer will be separated. Means there should be some extra layer will be formed, which is actually separate down the two different layer. You can observe the immiscibility between the two mixture. So the phenomenon is which macromolecular dispersion or mixing separate into two liquid layer is called the Quas-Svate. Two different layer will be observed. Okay, so the example here is the gelatin. Okay, gelatin and the acacia, they will not obviously mix together. So if I try to mix together, two layer will be formed, so they are immiscible. So upper layer having the low viscosity and the having the poor concentration of colloidal. Try to understand, the upper layer there is a immiscibility is observed. So upper layer they have little bit lower the concentration of the colloidal material, and the higher, those are in the lower layer, so they have little bit higher viscosity, as well as they will contain little bit higher concentration of the colloidal material. So that can be called as Quas-Svate. The which particle is in the lower layer, all those colloidal material, that is known as the Quas-Svate. Okay, and Quas-Svation can also be brought about by addition of the alcohol, sodium sulfate, macromolecular substances such as starch. Okay, mechanism may not be involved interaction of charged particle, but mechanisms such as dehydration of the solvated layer, in this case of alcohol. So if I add any kind of alcohol also in any kind of colloidal dispersion, in that cases also we can find this kind of extra layer will be formed and Quas-Svation each forms. Okay, so in that cases, what is the mechanism? Mechanism is dehydration, not the the charged particle interaction. This kind of thing will be not happen there. For if we add any kind of alcohol, so dehydration may be happen, and due to the dehydration, one extra layer will be happen. So by that, if I observe that two different immiscible layer we can observe from outside. Okay, that is the Quas-Svate formation. Okay, so Quas-Svate formation is not a, you can say like a stable formation or stable condition. Okay, from the colloidal dispersion point of view. Okay, so now the sensitization. Okay, so before going to the theory part, I want to just demonstrate you the picture that what is sensitization. You can see here that hydrophobic colloid have some positive charges, so these are stable. But if we add a small quantity, just particularly focused on the term, if we add the small quantity of the hydrophilic colloid, then that will be sensitization. Sensitization means it will be, coagulation will be happen there. Coagulation, if coagulation is happened, so means it will leads to the instability. Try to understand, in a hydrophobic colloid which is actually stable, if we add little bit small amount of colloid substance which is hydrophilic, then there is a sensitization actually happened. Sensitization means the coagulation is happened, and due to the coagulation, instability is we can formed. Okay, like say after sensitization, hydrophobic the colloid, they have the negative charge outside. Negative charge means a small quantity of hydrophilic colloid, and if we add the again some little bit concentration of electrolyte, they will coagulating down or hydrophobic जो colloid, that will actually get unstable. Okay, so this is the things regarding the sensitization. Sensitization is also is not a stable condition. Okay, so now just through the theory portion, in the presence of very small amount of hydrophilic colloid, the hydrophobic colloid may become more susceptible. They become more susceptible. Okay, they become more susceptible to precipitation from the electrolytes. So precipitation is the main terminology here. Sensitization is attributed to a reduction in the zeta potential below the critical value. The zeta potential will be reduced, and it is the reason that due to the reduction of the thickness of the ionic layer surrounding the colloidal particles. So it can be happened due to the reduction in the thickness of the ionic layer, because we have discussed in the interface there is a charge is present and outside the opposite charge will be present. This kind of the double layer will be formed. So due to this kind of sensitization, what happened, the thickness of the ionic layer that got reduced, and due to that you can find out the settle down, or you can find out the precipitation of this kind of colloidal dispersion. Okay, that is all about the sensitization. Okay, now the protection. So protection means this actually leads to the stability. Protection you can find, the call it like a little bit reverse case, like large. If you add the larger concentrations, here the smaller concentration is we have mentioned, but for the protection, if we protect any kind of colloidal dispersion, by the term only you can understand that we have to add the larger concentration of the hydrophilic colloid, and that will increase the stability of the hydrophobic colloid towards precipitation of the electrolytes. Okay, so obviously the colloid that will be gets some kind of stability due to this kind of protection, and the hydrophilic colloid adsorb means this is the only the interfacial phenomena, adsorb on the surface of the hydrophobic colloid and particles and form a protective layer, thus preventing them from precipitation. That is the important line. So that kind of extra layer that will protect this kind of thing to preventing them from the precipitation. Okay, if we add electrolyte, they will not undergo the precipitation. Okay, this phenomenon is called the protection. If we try to protect this kind of colloidal dispersion from the instability. Okay, the hydrophilic salt used for the purpose protecting the hydrophobic colloid known as the protective colloid. Okay, like you can see in the picture that here some positively charged stable hydrophobic colloids there. We have added a large quantity of hydrophilic colloid. So after that, obviously in the interface of this kind of hydrophobic colloid which are positive, in the interface the negative charge actually gathered down, and after that if we add the electrolyte, they will, after addition of the electrolyte, they will not precipitating down, rather they will redisperse properly, and the more stability can be observed. So protection is the reverse situation or reverse case for sensitization. Here after adding the large quantity of hydrophilic colloid, we can stable one hydrophobic colloid. Okay, so that is all about the protection. Hopefully you have got my point. And the last point is the gold number, and I want to mention that from GPAT point of view in 2024 GPAT, from the gold number the questions have came. So just clearly understand that gold number is the measure of the protective ability of the hydrophilic colloid. Simply that is the thing. The gold number is the measure of the protective ability, that in how much extent they can protect and they can give the stability to any kind of hydrophobic colloid. So that ability of any kind of hydrophilic colloid known as or denoted as the gold number. So this is defined as the number of milligram hydrophilic which when added in a 10 ml of the red gold salt prevents the change in color from red into violet on the addition of 1 ml 10% solution of sodium chloride. So this particular the statement and particular definition you have to remember, means the 10 ml red gold solution that prevents, and 1 ml 10% of the solution. The particular term you have to remember, the number. Okay, and now this kind of lower the gold number, higher the protective ability of the colloid. That is also important line. The lower the gold number, higher will be the protective ability of the colloid. Okay, gelatin is the most effective protective colloid. So you have to also remember that gelatin is the most effective protective colloid. So you can easily understand if it is effective protective colloid, So the gold number is little bit lower. So you can see in the example also, the gelatin, the gold number is 0.0052 to 0.01, albumin 0.1, acacia 1 to 5, and tragacanth is 2. I think if I am not wrong, from tragacanth the questions have came is 2024 GPAT. Okay, so you have to remember all this gold number because everyone is important, and gelatin, especially gelatin, as the gold number is lowest or least, the protective ability of gelatin is more effective. Okay, so this is all about the electrolytes effect and all those kind of the interaction of the colloid, and that was the last portion of our colloidal dispersion chapter according to the Bpharm syllabus. So that is all about. So today I have just completed the colloidal dispersions. So like if you have any kind of doubt, you can just ask me in the comment sections. So from the next classes we will just going accordingly to the syllabus. So thank you.